It's just that
So
so
we go through the final exam from last semester, and it will probably take us an hour and 20 minutes or something. I to go through the important questions. There are very straightforward questions that we will not go through. So like this question on memory management, so there is we can go through this as a warm-up question, but this is similar to assignment 4. So what you need to do is to just show how the frame allocation. So you have 3 frames and 8 pages, and first you have page 7. So page 7 will be in frame 0, then page 3 will be in the next frame, and page 5 will be in the next frame. And you are asked to do which replacement LRU. Then you have 7. 7 will just no change, no page fault, because 7 is already in physical memory. Then you have 4. With 4, we replace the least recently used, and the least recently used is what? 3. So we replace 3. So 7, 4, 5. Then we have 5, and 5 replaces the least recently used, and the least recently used here is what? 5. So 5 is already in physical memory, so we don't need to. 5 is already in physical memory, so there is nothing, no change. Then we get 1, and 1 replaces the least recently used. So the least recently used out of 7, 4, and 5 is what? 7. Okay, so 1 replaces 7. And then 2, we get 2. 2 replaces the least recently used. And the least recently used out of 1, 4, and 5 is 4. So 2 replaces 4. And finally 5 is already there. So the number of page faults, don't forget the number of page faults. So this is a question that I have been asking in all final exams. And just remember to put the number of page faults, which is in this case 1, 2, 3, 4, 5, 6. So 6 page faults. Okay, so this is a straightforward question, especially if you did assignment 4, then this should be very easy, but make sure that you get this, because most likely there will be a question like this in the final. Okay, now another question. So there are questions on calculations related to memory management and virtual memory. So, and again in your test there will be some questions like this. So the first question is on the effective access time. The effective access time with the TLB, effective access time is equal to the hit rate of the TLB. When you hit, you do only 1 memory access. And when you miss, you do 2 memory accesses. So this is the main formula for effective access time with a TLB. If you hit, you go to memory only once. If you miss, then you go to memory twice. Okay? So this is the concept. Now the question is, of course, you neglect the TLB access time. So there is an epsilon here and an epsilon here that we are neglecting. Okay. So calculate the TLB hit ratio that will keep the effective access time within 10% of the ideal effective access time. So, okay. So how do we do this? We want the effective access time to be 10%, within 10% of the ideal effective access time. Okay, so what should we substitute for effective access time? So we want it to be within 10% of the ideal effective access time. What's the ideal effective access time, which is defined for you? Ideal effective access time is the effective access time with no TLB misses. What's the access time with no TLB misses? That's just M. The effective access time when there are no TLB misses is M. So what should we substitute for this then? So this is just 1.1 M. Because you want it to be within 10%. You want this thing to increase the effective access time by 10%. So it's 1.1 M is equal to HM plus 1 minus H 2M, or 1 minus H M. And then we solve for what? We solve for H. So we get rid of M. And then 1.1 equals H plus 2 minus 2H, which is 2 minus H, which means that H equals 2 minus 1, 1.1, and that's 0.9. Okay. All right. So this is one question. There will definitely be calculation questions on memory management, and make sure that you understand the concept. So the questions are going to be different than this. So there will be questions that I want you to think about. So the whole point is to make you to test your understanding, your actual understanding of the material, and to get you to think. So there will be questions like this, but different questions. So make sure that you understand the concepts. A program has a loop that is executed 500 times. The code inside the loop sequentially accesses a large array that spans 100 pages. So this is similar to the sequential access example that I used in class. Each page has 200 words. The page replacement policy is LRU. Calculate the page fault rate for the execution of the entire loop in each of the following cases. Okay. So the page fault rate. What's the page fault rate? So the page fault rate, in general, equals number of page faults divided by number of memory accesses. So how many memory accesses resulted in page faults? Not the number of page accesses, number of memory accesses. Now what's the difference between memory accesses and page accesses?
Page access go to virtual memory, while memory access has to go to physical memory.
No. It's the same thing. Well, it's all in virtual memory. But in terms of counting, what is a memory access and what's a page access? A page has multiple memory locations. So here the question is saying the page has 200 words. So each page, this is a page. The question is saying the page has 200 words. Always keep in mind that the page is not just one memory location. It's not just one word. It's not just one array element. It's not just one variable. It's not just one instruction. The page is a page. It has kilobytes of data. So in this case, in this example, it's telling you that the page has 200 words. Okay, so let's see how we are going to calculate this. Now, the first part of the question, the process has 120 frames, and there are 100 pages. Now, how many page faults will we have in this case?
0.
No. We will have page faults. The number of frames is greater than the number of pages. So the number of page faults that we will have is going to be only the first loop. So the first iteration of the loop. In the first iteration of the loop, everything will result in a page fault. Then, in all subsequent iterations, everything will be in physical memory because we have more frames than we have pages. Okay? So the number of page faults in this case is going to be just the number of pages, which is 100 pages. Number of memory accesses. So number of memory accesses is going to be 100 pages, and each page has 200 words in it, and this will be executed 500 times. So this is the number of memory accesses. This is the number of pages. This is the number of memory accesses in each page. And this is how many times each of these will be repeated. So everything will be repeated 500 times because it's inside the loop. While the page fault will happen only in the first iteration of the loop. And the page fault will happen only once per page. Okay? So the page fault happens only once per page, not once per memory access. That's a key idea, in memory management. You have this page with 200 words. Once you load the page in physical memory, all of these accesses are not going to result in page faults. Right? So this is a key idea in memory management or in paging. You get? Once you bring the page, then all accesses to the same page are not going to result in page faults. Okay, any questions on this? Okay, so this is the page fault rate for the first part. For the second part, this is part 1, part 2, page fault rate. Now, you have 80 frames and 100 pages. In fact, for you, this is going to be easy because this is the example that I used in class. But last semester, I did not use this example in class. So, in fact, the question was meant to test how many students are going to figure out that every single page access is going to result in a page fault here. So, because I have used this example in class, for you it should be obvious. Because we did this, with least recently used, you have only 80 frames. In fact, you will get every page will result in a page fault with any frame count that is less than the number of pages. If the number of frames is less than the number of pages, everything is going to result in page fault with least recently used. Because, well, these are the pages, so you'll use your frames. Say at this point, you have used all the frames, you have less frames than pages. Now you will need a replacement. When you replace, you will replace this with least recently used. So you will replace this and you will lose it. When you get back to it in the next iteration, you will not find it. So when you get to this, you will replace this. So you'll keep replacing things so that when you get to them in the second iteration, they will no longer be in physical memory. And this will happen in this particular pattern. When you have a loop, when you have sequential access to an array, and least recently used, and the number of frames is less than the number of pages. Every single page access will result in a page fault. So in this case, the number of page faults is going to be multiplied by 500. And the number of memory accesses is the same. That's not going to change. Okay. So basically the point here is that if the number of frames is less than the number of pages, the page fault rate will get multiplied by 500, which is the number of iterations of the loop. Okay. Okay, according to my priorities, I'm gonna go to question 6 because it has some questions that are more interesting. Okay, so question 6 is on assignment 2. So here I'm giving you some of the code for assignment 2. And first question, replace x1, x2, x3 with the right values or expressions. So some x1 waiting on one of the semaphores. So in assignment 2 there are 2 semaphores. One is the mutual exclusion semaphore and one is the notification semaphore, the one that notifies the parent. And of course, here, I'm testing you on assignment number 2. So if you have done assignment number 2, then you should go through this very quickly. You should understand what each semaphore means. Okay, so in this case, which one is the mutex semaphore and which one is the notification semaphore? Well, this is the semaphore that the parent will wait on. So which one is that? So we look at the child and see which semaphore the child posts when it finds a 0. So this is the semaphore that the child posts when it finds a 0. So this must be the notification semaphore. So now we know that semaphore 1 is the notification one. So now we know that semaphore 1 is the notification, notify parent, and semaphore 2 is the mutex, semaphore to protect the shared variable. Okay, so this means that the answer to x1 is semaphore 1. X2 is the condition that the child will check on. So if this is true, it will notify the parent, and basically, what will cause it to say that it's done, and the minimum is a 0. So it's just finding a 0. So x2 is going to be data of I equals 0, and x3 condition x3 is the condition under which the child will notify the parent. So it's incrementing the thread count. So it's going to notify the parent under what condition?
If all the threads have completed.
Yeah, so what will be the condition then?
G thread count equals to.
So G done thread count equals G thread count. So this is the condition. Sorry, equality. This is equality checking. So this is the condition. Okay. Second question. What's the advantage of the semaphore-based solution implemented by the above code relative to the solution in which the parent continuously checks on the children in a busy waiting loop? Under what conditions will the performance difference between the two solutions be most pronounced? Okay, so what's the difference between the two solutions? And under what conditions we will see a more significant difference between the two? So this is something that you're supposed to have written in your report for assignment 2.
Save the CPU.
You should have written this in your report for assignment 2. So this should have been one of the observations.
Would it be
Yeah.
wasted cycles on the part of the busy waiting loop?
Yeah. So it's the semaphore puts the parent in the waiting state, so it doesn't use CPU cycles, while when the parent is checking in a busy waiting loop, it's using CPU cycles. So under what conditions will the difference be more measurable?
A single CPU?
Well, yes, but we ran this program on a multi-core CPU, so it's not, that's true, but it's not the interesting case. Yeah.
If the answer is towards the end, if the value you're searching for is towards the end of the list.
If the value is towards the end,
Yes.
well, so you are saying that if the value is close to the end, well, the 0, you mean?
Yes.
The 0 is close to the end, then the parent will be spending more time checking on the children.
Yes. If you have it towards the beginning, they have similar times because there's not many wasted CPU cycles. Versus if it's towards the end, busy waiting for 1,000 elements is going to take a much longer time than busy waiting as you search through 2.
Okay. Well, but there is a more important factor. That's true. What you are saying is right.
So it may have to do with the number of processors. If there are
Yeah.
more processors and there are children and parents, then they can just run in parallel, and then you're not wasting any CPU time having the busy waiting
Okay.
loop. But if you have fewer processors, then the busy waiting loop will be competing for the processors with the other processors.
Okay, so what should the numbers be? So what's the precise condition? The precise quantitative.
The number of core equal number of flash.
The number of
Cores equal to
the number of
flash.
cores.
It's equal to or less than the number of.
Yeah. So if the number of cores is less than or equal to the number of children, then the parent will be competing with the children for CPU time. Otherwise, if the number of cores is greater than the number of children, there will be a core for the parent. So the parent will be running on its own core, and it will not be competing with the children, and it will not be the CPU cycles that the parent will be using will not be measurable. Okay. Now, a question on calculating the speed up from parallelization. Okay, so this question is telling you that basically calculate the speed up or the ratio between the time. The speed up is always equal to speed up equals the sequential time divided by the parallel time. So when we talk about speed up, we divide the sequential time by the speed up from parallelization is equal to sequential time divided by parallel time, because we expect the sequential time to be greater. So if the sequential time is 10 and the parallel time is 5, then our speed up is 2. The speed up should be a number that we expect to be greater than 1. Okay, not like because many people in the midterm they gave numbers less than 1 for speed up, like a speed up of 0.5. This is slow down, not speed up. So speed up, you divide the slow by the fast. Slow divided by fast. That's the speed up. The ratio between slow and fast. Okay, so now what's slow? Now with sequential, now it's giving you one piece of information that the search part of the sequential program takes 80% of the program's execution time if the input array has no zero. So if you go through, if the array has no zero and you have to go through the entire array, then that part takes 80% of the program's time, and 20% of the time is just parsing the command line arguments and generating the input data. Now, what does this piece of information mean? That 20% of the time is spent in parsing the command line and generating the data. What does this mean? Yeah.
That running any parallel activity wouldn't affect it. So that's a hardcore amount of time that has to stay.
Yeah, exactly. So this means that this 20% is there in both cases, with the sequential and with the parallel. Basically, this is the part that we cannot parallelize. We cannot parallelize this. You'll have to execute it anyway. So that's why you will have this 0.2 in the numerator and denominator. Now, plus the search time. Now, what's the search time when you do sequential, but the parents waits for all children, no semaphore is used, and there is a zero at the end of the third division. So you have here, it's saying that you have 4 divisions, right? 4 divisions. And you have a zero here. 1, 2, 3, 4. So if you have 0 here, with the sequential part, even the sequential part should terminate as soon as it finds a 0. So this time is 3/4 of the time when there is no 0. So it's the time when there is no 0 is the 0.8, but when there is a 0, you only go through 3/4 of this array. So it's going to be 0.8 multiplied by 3/4. Now, in this case, when there is a 0, the parent waits for all children. When the parent waits for all children, what will be the time for the parallel program?
For the quarter?
Yeah, it's going to be 1/4 of 0.8. Yeah, exactly. So it's 0.8 multiplied by 1/4. Because the whole point is that you will be executing these in parallel. So it's going to be like, so this is sequential. Parallel is like this. 1, 2, 3, 4. So this is parallel. So this is 1/4 of the time. So you calculate this. So this is 0.2 plus 0.8 divided by 3/4. So this is 0.6 divided by 0.2 plus 0.2. And this is 0.8 divided by 0.4. And this is a speed up of 2. You always check whether the final answer makes sense or not. So this is the speed up of 2. So intuitively, the sequential program will take 3/4 of the time, and 3/4 of the array, while the parallel will scan 1/4, but it will scan 4/4 in parallel. So it's like scanning 1/4. Of course, this is ideal parallelism. We're ignoring all kinds of overhead. Okay, so now what will happen in the second case? Semaphores are used, and there is a 0 right at the beginning of the 4th division. So how will we change the calculations if we are using semaphores and there is a 0 right at the beginning of the 4th division? Now what will be the time? So the speed up will be, so the sequential will not change. It's going to be 0.2 plus 0.6 divided by 0.2 plus what?
Zero.
Hmm?
Zero.
0. Exactly. Ideally, with all, ignoring all the overhead, if you are doing these in parallel and one of them has a 0 right at the beginning, then you are doing this in 0 time. Okay, so you only have the overhead time. So this is going to be 0.8 divided by 0.2, and that's 4. So now it makes, we expect this to be more speed up. So this is 4 times faster, because in this case, it will not be executing these in parallel. In fact, it will just find this 0 and then everything will terminate. Okay. Okay, I think we are doing well. Modify the above code to minimize context switching by limiting the number of child threads in the ready queue to the number of cores. Let the number of cores be k if k is 4 and there are 6 child threads. Only 4 of them will run and the other 2 will wait. When one of the 4 threads is done, one of the waiting threads will become ready, and so on. Okay. So what's the solution here? How do we limit the number of children in the ready queue? Limit that to the number of cores.
Semaphore.
Yeah, we use a semaphore. What kind of semaphore?
Downtown.
Yeah. So this is a direct application of a counting semaphore. So we just we create a semaphore, let's call it limit, and we set it to k. We initialize it. With semaphores, whenever you use semaphores, make sure that you specify that initial value, because the initial value can make a huge difference. In fact, here, the whole point is in the initial value. So, the initial value here is the key, right? So, and where do you put this? Just you put at the beginning and at the end of the child. So in the beginning of the child, you put wait here, you put wait on limit, and you post it when you are done. So when you are done, you have to be careful because you also exit here. So the child can exit whether it finds a 0, when it finds a 0 or when it's done. So you need to post it here and here. So just wait on limit, post limit here, and post limit here. So this is just a direct application of counting semaphores. Questions?
I'm sorry, I missed it. Where was the second post? Second.
So you post it when you are done. When is the child done? So when it exits here, of course you must post it before you exit. So before the P thread exit, and you post it at the end here. You can do it before this, after this. Even if you do it, you should do it after. Okay. Okay. So the last question is changing the synchronization problem. So this is a different, changing the search problem to a different problem. Now we need to, to read this and then understand the problem and solve it. I've seen students in the final who would just, write the solution to the problem that we did in the review session. So this is not going to be on the test. Okay, so the test there will be a different problem. So don't waste your time. There are students who waste time. I don't know why. They just think that I'm going to ask you the same question, and they just waste a lot of time just writing the solution to this. So we will write the solution to this in order to understand it. But on the test, there will be a different problem. So the whole point is to test your ability to read this, digest it, and design a solution. That's the point, not test your ability to memorize the solution or write it in your cheat sheet. By the way, you'll be allowed to have a cheat sheet in the final. So so don't write solutions in the cheat sheet. Write key information.
Single or double-sided?
Yeah, you can write on both sides.
Okay.
Yeah, that's. Okay. So here. Okay. So let me. So I assume that.
Can we print our cheat sheet, Professor?
Yeah. You can type it. Yeah, you can print. You can use any font.
Excuse me. Thank you.
Okay. So the idea here is you search for a key, and you'll assume that there is a specific key in the array, and the objective is to check if the number of occurrences of that key is greater than or equal a certain target. So if the key equals 5, then you want, and the target count equals 9, the objective is to check if 5 occurs 9 times in the array. Okay. So now it's describing the solution as the child threads each child, you'll divide the array into a number of divisions, the same way we did in the assignment. That doesn't change. And each division will check for the key, and it will notify the parent whenever it finds an occurrence of the key. So the child will notify the parent whenever it finds an occurrence of the key, and it's the responsibility of the parent to keep track of the number of occurrences and terminate as soon as the target has been met or the search is complete. And the parent should terminate the search as early as possible. So if the first 9, or if the, let's say if the 9 occurrences are detected early, then we should terminate as soon as we find 9 occurrences of the key. Okay? All right. So now the children will have to update a global variable. G, let's call it current count, which is initialized to 0. So this keeps track of the current count, and each thread will increment this whenever it finds an occurrence of it. Now, when I say this, that there are threads that will be updating this global variable, what will be the first thing that comes to your mind?
Mutex. You need a mutex around
Yeah,
it.
exactly. We need a semaphore or a lock to protect it. So this is the most fundamental idea that we have learned in chapter 5. Whenever you have multiple processes or multiple threads accessing a shared variable, you must protect access to that shared variable using a semaphore or a lock. So this is one idea, that's a key idea that you shouldn't miss, that you should protect access to this with a semaphore. So we will declare semaphore, let's call it, because I think we already have a mutex here. What is it called? They're called semaphore 1 and semaphore 2. Okay. Okay, so we'll call it semaphore 3. And we initialize it to what? What do we initialize a mutex semaphore to? 1. Mutex semaphores are initialized 1. And this is a mutex to protect G current count. Okay? So it's a good idea to write comments. So this is the mutex to protect the G current count. And then we keep the other semaphore, semaphore 1 and semaphore 2. So semaphore 1 is for notification. We keep them, the existing semaphore, semaphore 1 for notification. And semaphore 2 is a mutex to protect what? To protect the done thread count. Done thread count. It's thread, but I just write it. THD here. Okay. Now what do we need? So let's do the child. Or let's think about the overall structure. So now, unlike assignment 2, where the parent will get only one notification from the children, here the parent will get multiple notifications from the children. So this is, I think, this is the fundamental difference. The parent will be getting multiple notifications from the children. So how should we do that? And we don't want the parent to be wasting cycles. So we want the parent to be waiting on a semaphore. So when it says we don't want the parent to be wasting cycle, that means we want the parent to be waiting on a semaphore. So we want the parent to be waiting on a semaphore, but it will be receiving multiple notifications. So how can we do that? So we just put that wait in a loop. We will put the wait in a loop, and we break out of the loop when the termination condition is satisfied. So in this case, the termination condition is finding the target number of occurrences, or all threads are done. So the parent will have a loop while not done. Now done is a Boolean. Boolean done equals false. While not done, wait on the notification semaphore, which is semaphore 1. Wait on semaphore 1. And then check on the value of the target count if it's equal to the current count is equal to the target count. So if current count equals target count, if the current count equals the target count, then we know that the target is met. So we need a variable to indicate that the target has been met. So we call it Boolean met, which is equal to false. So met equals true. And we just set done to true, because we are done. So if this is the case, we have met the target, and so I'm writing pseudocode here. So the indentation here is significant, but you can write in braces. Okay. So this is if the target is met. What's the other condition for termination?
You didn't find it. You didn't find.
How do we know that? Yes. Yeah, all the threads are done, exactly. So if G done thread count equals G thread count, then we are done. Done equals true. And if we are done, we will exit out of the loop, and then we print met. print the value of met, whether it's true or false. Okay, so this is what the parent does. Now what does the child do? So the child will have that loop for I equals start, I less than or equal to end, I plus plus, and it will check if G data of I equals what?
Key.
Equals key. G key. If it's equal to the key, then we need to notify the parent. And we notify the parent by posting the notify semaphore. So we post, well, before we post, what should we do?
Decrement.
What should we do before posting? What should the child do before posting the semaphore? Yeah, increment the current count. So we need to increment the current count, but the current count is a shared variable. So remember, the key idea is whenever a process or a thread accesses a shared variable, you need to protect that. So we protect this by waiting on the semaphore that we declared for protecting this, which is semaphore 1. Semaphore 3. Waiting on semaphore 3, increment G target G current count plus plus, and then post semaphore 3, and then post semaphore 1. So these semaphores are for protecting the shared variable, and this semaphore is to notify the parent. Notify parent. And then what else does the child need to do? In fact, the last part of the child will not change, which is this. So in fact, we don't need this here. Thread done, we don't need this array. So we can skip this, but this part will not change. So lines, by the way, and you can do this in the test, where if certain lines do not change, don't waste your time rewriting them. So you just say lines 14 through 18 stay the same. So I'm gonna say lines 14 through 18 stay the same. Is that right? Let's check this. Yeah, done thread count incremented, and it's protecting the semaphore. And then, no, well, there's a change. So in fact, they will not be the same. So, okay, so without line 16. So we need to remove the condition. Now we unconditionally notify the parent when we are done. So, okay, so line 16 goes away. So lines 14 through 15 stay the same, and lines 16 through 18 stay the same. Yeah, posting the semaphore 1. Yeah, posting semaphore 1 can be done after posting semaphore 2. It doesn't matter. You can do semaphore 1 and semaphore 2 in any order. But you will need to remove this condition, because here the child is notifying the parent whenever it's done. It doesn't have to be the last child. Unlike the assignment 2, here the parent will be receiving multiple notifications. Stay the same. Question? Someone had a question? Okay, so this type of question, always don't start with this question. So leave it and work on it at the end when you are done with all other questions. And try to get the low-hanging fruits. So there, the question, the exam will has questions at different levels of difficulty. So try to get the easiest questions first. Okay, so should we take a break or continue? So let's continue. I've already covered the most important questions. So I need okay, another important question, which is straightforward, but I'm going to go through it because to remind you of this, because I see that many people have forgotten this. So there will definitely be a question on scheduling, and one question will be on regular scheduling, and another question will be on real-time scheduling. So I'm not going to go through the regular scheduling because we went through so many of them, and I assume that you have done assignment 3. If you have done assignment 3, this should be a piece of cake for you. Make sure that you cover all the algorithms that we have covered in class. Okay, I will do the earliest deadline first, not because it's tricky, but because just to remind you of it, because I think many people have probably forgotten this. So let's go through it to review it. By the way, in real-time scheduling, there are 2 algorithms. There is the earliest deadline first, and then there is rate monotonic. And I think, most likely I've been having this question on real-time scheduling in every final. But some sections get the earliest deadline and some sections get the rate monotonic. So make sure that you cover both. And since I have 3 sections this this semester, so 2 sections will get earliest deadline and 1 section will get rate monotonic. Yeah, so but you don't know which one will be. So you need to prepare for both. Okay. In fact, earliest deadline is requires more work. So what's the idea behind earliest deadline? So whenever we need to make a decision, we calculate the deadline for each process and give the CPU to the process with the earliest deadline. So this is the Gantt chart or the timing diagram. So at time 0, make sure that you put the deadlines. Show your work. Here it emphasizes that. Where does it say that? Where do I say this? Write a comment justifying the scheduling decision made at the arrival of every new CPU burst. So whenever a new CPU burst arrives, we need to calculate the deadline. And in the beginning, deadline of P1 equals the deadline of P1 equals 30. Deadline of P2 equals 20. So which one gets the CPU? P2. So P2 gets the CPU. For how long? It will get the CPU for 10 time units, and it will finish before the second CPU burst of any of the processes arrives. So, or the second burst of P1 arrives. So it will get it until time 10. And at time 10, P1 will get the CPU. And then, when do we have to make the next decision? At time 20. At time 20, we make a decision. So we just look at the deadlines. So calculate the deadlines. Deadline of P1 equals deadline of P2 equals. What's the deadline of P1 at this point?
30.
Still 30. Deadline of P2?
40.
40 because we have a new burst of P2 arriving here. Okay? So who wins? P1. So P1 gets to keep the CPU until time 25. So this is time 25. Then P2 gets the CPU. Then when does the next decision have to be made? At time 30. So at time 30 I have to make a decision because I have a burst of P1. Now deadline of P1 equals deadline of P2. Deadline of P1, a new burst, so what's the deadline now?
60.
60. Deadline of P2 is still 40. So P2 wins, so it keeps the CPU. And P2 has a CPU burst of 10, so it's going to be until 35 when P1 gets the CPU again. And at time 40, I will have to make a decision again because there will be a new burst of P2 at time 40. The deadline of P1 equals 60. The deadline of P2 equals 60. The deadline of P2 also equals 60. Oh yeah, it's specified. So it's if at some point both processes have the same deadline, resolve the tie in favor of the process that currently has the CPU. Okay. So it's the question is telling you what to do, and you resolve it in favor of process process P1, which has the CPU. So it will keep it, and process P1 has a dead 15, so it's going to be on time 50. And I think the question is asking you to stop at time 60. So time 50, P2 gets the CPU. And at time 60, there will be a new cycle arriving. So this is earliest deadline first. Any questions? Okay. So there is a question on deadlocks. The deadlock question is very straightforward. The only thing that you have to pay attention to is detection versus avoidance. So you want to make sure you do the right thing, detection or avoidance.
Real quick, Professor?
Yeah.
Are the comments that you wrote there sufficient if we do a similar thing?
Yeah. So just put just specify the deadline so that I know, that you know what the decision is based on. It's not just guessing. Okay. Okay. So the deadlock, there will be a question on deadlocks, and it will be straightforward, but be careful. Some sections will get detection, and some sections will get avoidance. And so you have to be prepared for both, and make sure that you do what's required. Make sure that you read the question. So we did memory management. So there is a question on disk allocation. You will not have this question because we did not cover this semester. So you will not have a question like question 5. In fact, this is the only topic that we did not cover this semester. So you will not have a question like this. Even though it's a very easy question, by the way. So maybe it's unfortunate that okay, so let's go through some of the multiple choice. Maybe I think we can go through them quickly. Okay, so the multiple choice questions are good for reviewing many different topics. So the lesson that I hope that everyone has learned from the midterm is reading the question carefully. So read the question carefully. Don't just circle the first answer that looks right, because there may be multiple right answers, and the right answer may be one of these combinations. Okay. Okay. What's the relation between page size and fragmentation? A larger page size decreases internal fragmentation. Well, first of all, does the page size affect internal or external fragmentation? No, internal. It affects internal fragmentation. Internal fragmentation is what is affected by the page size. Because no matter what the page size is, you don't have external fragmentation with paging. When there is paging, there is no external fragmentation, regardless of the page size. Page size affects internal fragmentation, and clearly, the larger the page, the more internal fragmentation you have. So, a larger page size increases internal fragmentation. So the answer is C. A logical address space of a process has 512 pages with 8 kilobyte page size. How many bits are required in the logical address? So the logical address will have a page number and an offset within the page. So the page number will require how many bits? There are 512 pages. So 512 pages, 512 is 2 power what? 2 power 9. 512 is 2 power 9. So page number requires or needs 9 bits. Now the offset needs, the offset within the page depends on the page size. So the page size is 8K. 8K is 2 power what? 2 power. So 1K is 2 power 10. 8K is 2 power 13. 2 power 13. So the offset is going to be 13 bits. So logical address is 20. Okay? So it's 9 plus 30. Which of the following is not true? So here, when it asks you about what is not true, be careful. Don't mark something that is true. So maybe you can put a small check on the ones that are true, then decide which one is not true. Paging divides memory into equal blocks. This is true, right? Segmentation may divide memory into unequal blocks. This is also true. A single instruction may access multiple pages. True or false? True. True, because we have shown examples. And in fact, any instruction, because an instruction may access code and data. So an instruction may access multiple pages. That's true. A single operand can never access more than one page. A single operand can never access more than one page. Is this true or false? This is false, because we have shown examples of one operand accessing multiple pages if there is indirection. Right? Remember indirection? When there are if it's a pointer, then it may access multiple pages. So a single operand can never access one page. This is not true. If both segmentation and paging, in both segmentation and paging, the address space of a process does not have to be contiguous. That's true. A process can run even if only a small subset of its pages are loaded in physical memory. This is absolutely true, because that's the whole point behind virtual memory. So the only thing that is not true is D. And in fact, with questions like this, if you are 100% sure that A, B, C, E, and F are true, then you know that the answer is D, even if you have some question mark. But if you are certain that the others are true, then you know that the one that you are not certain is true must be the one that is not true. Which of the following is true about a page fault? Implementing a page fault does not require hardware support. Of course not. Page faults require hardware support because we need the hardware to give control to the operating system when the page fault happens. Handling a page fault always involves transferring data from disk to memory. Yes, because you will always transfer from disk to memory. Handling a page fault always involves transferring data from memory to disk. I did the other way. So we always transfer from memory to disk, but from disk to memory is what we may or may not do, depending on whether the page that we are replacing has been modified or not. Okay? So this is something that we may not have to do, so it's not true. Page faults occur infrequently due to locality of reference. This is a very important fact, right? A key idea in virtual memory. So this is not true. A is not true. Does not require is not true. Handling a page fault always involves transferring data from disk to memory. This is not true. C is true. We always if I had this in a test, I would have gotten this wrong. Okay, so again, we always transfer. So this is memory, and this is disk. So in which direction do we always transfer? From disk to memory. Because this is handling the page fault. We always transfer from disk to memory. This is a maybe, depending on whether the page that we are replacing has been modified or not. So handling a page fault always involves transferring from disk to memory. This is true. And page faults occur infrequently. D is true. So B and D are correct. Okay. Yeah, questions? Which of the following is true about page replacement policies? LRU always gives the best performance among all replacement policies. True or false?
False.
False. Because optimal is the one that gives the best performance, and we have seen an example in the loop. LRU did not do well in the loop. It gave page faults all the time. Optimal page replacement is theoretically the best, but is impossible to implement in practice. This is true. Yeah. With first in, first out page replacement, increasing the number of frames may increase page faults. Yeah, so this is Bilady's anomaly. So this is true. With LRU page replacement, increasing the number of frames may increase page faults. No, this is not true. So maybe this is something that I did not emphasize in class, but Bilady's anomaly can be seen only with first in, first out, among the ones that we have studied. So it cannot happen with LRU, it cannot happen with optimal. And I think this is somewhere in the slides. You will see this somewhere in the slides. So this is not true, this is true, B and C are true. Okay, so B and C. The answer is B and C. What's the difference between scan and C-scan disk scheduling algorithms? So remember, scan is the one that scans in both directions. C-scan is the circular one that services requests in one direction, but when it moves back, it doesn't service any requests. So it has nothing to do with reaching the end. So reaching the end versus not reaching the end, that's the difference between what and what?
Look.
Yeah, look and scan. So look is the one that doesn't reach the end. So the difference between scan and C-scan has nothing to do with reaching the end. It has to do with whether we service in both directions or in one direction. Scan services requests when it's moving in both directions, while C scan services requests only when it's moving in one direction. This is the right answer. So C is definitely not right because it's the opposite. C scan always results in a smaller average seek time than scan. No, none of them has been proven to result in, to always give a smaller average seek time. So we said that each one of them has advantages and disadvantages. So the answer is B. Which of the following is true about starvation in disk scheduling? So which algorithm causes starvation?
The shortest.
Yeah, the shortest seek time first, exactly. So shortest seek time is the only one that causes, among the ones that we studied, that may cause starvation. First come, first served can never cause starvation. Is that true?
Yeah.
Yeah, it's true. Because first come, first served. So you are guaranteed to get serviced in order. So this is, from starvation point of view, first come, first served is the best. Scan doesn't cause starvation because the waiting time can be long, but will always be bounded. Is that true?
No.
Well, it's true. It doesn't cause starvation because scan is scanning. So it's not like shortest job. It will not get stuck. Scan will always make progress. It can never get stuck like shortest seek time first. Shortest seek time first can get stuck if shorter requests keep arriving. But scan will always scan, which means that the waiting time for some requests can be long, but they will eventually get serviced. Look and see look may cause starvation. No. All the scan type of algorithms cannot cause starvation. Okay. So this is true. B is true. Scan doesn't cause starvation, and C is true. Okay, so A, B, and C. So the answer is A, B, and C are correct. Which of the following is true about the difference between round robin and the shortest job first scheduling algorithm? So here I'm referring to CPU scheduling because that's where we study round robin. So shortest job first minimizes the average waiting time, but round robin does not. Yeah, this is true. Round robin minimizes the average waiting time, but this is definitely wrong. Shortest job first gives better responsiveness than round robin. False. Yeah, round robin is the one that gives better responsiveness. Shortest job first does not cause starvation. False. Okay, so this is false, and the only one that is true is A. Shortest job first minimizes the average waiting time. What's the difference between rate monotonic scheduling and earliest deadline first scheduling? Earliest deadline is preemptive while rate monotonic is not? No, they're both preemptive. So if you review these algorithms, you will see that both are preemptive. Earliest deadline assigns priorities while rate monotonic does not. No, this is not true. Both assign priorities, but they assign different priorities. Rate monotonic is less likely to cause a process to miss its deadline. So, no, in fact, it's the other way around. Earliest deadline is less likely to cause a process to miss its deadline because it's the one that looks into deadlines. Rate monotonic does not look into deadlines. So this is not true. Rate monotonic uses fixed priorities while earliest deadline first dynamically adjusts priorities. So this is true. This is the difference between them. How does contiguous disk allocation compare with linked disk allocation? Contiguous provides faster random access, while linked provides faster sequential access. No, linked, linked is not, in terms of, remember, contiguous and linked. Contiguous is good for both random and sequential access. But linked, the advantage of linked over contiguous is what? What's the biggest problem with contiguous? Fragmentation. So remember, the same problem seen in disk and memory, contiguous has a fragmentation problem. So the problem with contiguous is fragmentation. Linked does not have that problem. Okay. So A and B are both wrong. It's just contiguous is better in terms of access time. Linked provides faster sequential and random access but causes external fragmentation. In fact, it's the other way. In fact, if this had been contiguous, it would have been true. Contiguous provides faster sequential and random access but causes external fragmentation. So if this had been contiguous, it would have been true. So it's wrong. Contiguous provides faster sequential and random access but causes external fragmentation. So this is the answer, D. I didn't realize that it's one of the options. Okay, if a process uses 1100 bytes of memory in a system with a page size of 512, what's the size of internal fragmentation? Okay, so again, be careful with this because it's easy to make a mistake. So 1100. So 1100 we will get, 1024 is going to be 2 pages are not enough. So we need 3 pages, right? Because 1024 is the closest, it's not enough. So we need, it's 512. So this is 2 pages. So we need 3 pages. And 3 pages is what? 1024 plus 512. And that's 6351. Okay? So that's what we will be using. And this is the size. So the wasted space is the difference. 1536 minus 1100, that's 436. Okay? So again, be careful with these calculations. It's not tricky and it's not hard, but you have to be careful. How does indexed disk allocation compare with FAT-based linked allocation? So the difference between indexed and FAT-based. Indexed may waste a substantial amount of disk if there are many small files. Yes, this is true. That's one of the biggest disadvantages of indexed, because the index reserves the whole block, and if the file is small, we are wasting lots of space. Indexed allocation causes more external fragmentation. So in terms of fragmentation, indexed and linked are the same. They both can use any block on the disk. They are not contiguous. So as far as fragmentation is concerned, indexed and linked are the same. But the difference is in how they are, how the indexing is done. Linked allocation with FAT causes more external fragmentation. So both B and C are wrong because they are the same as far as fragmentation is concerned. This linked allocation with FAT provides faster random access. So which is faster, linked with FAT or indexed for random access?
Index.
Index, because for random access, indexed you go straight to page number, block number 500. While to go to block number 500 with the FAT, you'll have to traverse the link. It's a link only in the FAT table, but you'll still have to traverse the link. Okay, so Okay, so which one is correct? Indexed allocation, A is the only one that is correct. A is the only one that is correct. Okay, which of the following is or are true about working set size? So the working set size, a larger working set size increases the page fault rate. Is that true or false? It increases the page fault rate because larger working set size means that you need more pages. So working set size is the number of pages needed. So when processes need more pages, that increases the page fault rate. A larger working set size decreases the page fault rate. It's the other way around. If the working set sizes of all processes exceeds, well, this should be, the sum of the working set sizes of all processes exceeds the number of available frames, the system will thrash. Yeah, so this is the key idea in working set size and thrashing. If the sum of the working set sizes of all processes exceeds the page fault rate, the number of available frames, then the system will thrash. The working set size of a process does not change with time. Is this true or false? True or false? This is absolutely wrong. Because we said that a process goes from one locality to another. If a process is executing one loop in which it's using 5 pages, it may move to a different loop in which it's using 1,000 pages. So one of the important, remember that graph where the process goes from one locality to another? So this is not true. This C is true and A is true. Okay? So A and C. Which of the following is true about storage allocation algorithms? Best fit gives better utilization than worst fit, and first fit in all cases. No algorithm gives best results in all cases. First fit and best fit have been found to give better utilization on average than worst fit. Yes, that's true. So B is true. Worst fit gives worse utilization than first fit and best fit in all cases. No, this is not true in all cases. We did not study anything that is true for all cases. First fit is always faster than worst fit and best fit. No. So the only thing that is true is B. On average, or experimentally, first fit and best fit perform better than worst fit. But we can't make any judgment about all cases. How do processor affinity and load balancing interact in a multiprocessor environment? So, processor affinity and load balancing. Improving load balancing always satisfies processor affinity. No, in fact, they conflict with each other, or they may conflict with each other. So, they may conflict because the key idea is that in order to balance the load, you may have to move processes from one processor to another. And when you move a process from one processor to another, you break the affinity requirements. So to balance, you must keep moving processes around, and that's against affinity. But it's not all the time. It's in some cases. So improving load balancing may conflict with processor affinity requirement in some cases. Yeah, so you have to be careful about statements that are made about all cases and some cases. So this is in some cases. We can't say that this is always true. But in some cases, load balancing conflicts with processor affinity. Okay, so processor affinity and load balancing always conflict with each other? No, not always. Okay. because you may not need to move processes around. If you have two processes and they are running for a long time, you don't have to balance and you don't have to break the processor affinity. So it's not always that they conflict. Okay. All right. So any questions?